let's start. I don't know if you remember 2 units ago when we were looking at VI equals or VF equals VI plus AT and D equals VIT plus a half AT squared. I said to you during that unit that lessons 3 and 4 were the most important ones. If you wrapped your brain around those, everything else would kind of fall into place. For this unit, lessons 1 and 2 and 3 are the most important ones. So we're going to get about 2/3 of the way through the first lesson today. So you want to kind of buckle up. It's going to be a lot of conceptual stuff. One of the things you might look at on your green sheet, the unit that we're in is called forces. You may notice there's only 3 equations listed there. It's actually several thousand equations. I can't list them all. What I'm going to be teaching you how to do, Tristan, is derive everything yourself from scratch, which is going to be one step further removed from what we were doing with kinematics. So let's jump on in. It says this. Kinematics, which was displacement, velocity, v initial, vf, time, etc., that was the study of how things move. We're now going to look, Darian, at dynamics. Dynamics is the fancy word for forces. And forces is the study of why things move or don't move. We need to start out with a definition of what a force is. I'm going to say that a force is a push or a pull. That's actually a terrible physics definition. A physicist would say a force is an interaction between two objects when they exchange leptons. I'm not going to dive down to the quantum level for everything, Cole. We're going to say, you know what? If you're pushing on something or pulling on something, you're applying a force. Is force a vector or a scalar? It is very much a vector. Direction very, very much matters. I'll prove it to you in just a second. Sorry for those of you on YouTube, you're not going to see this demonstration. What would be a good symbol to use for force? We're going to use a capital F. Forces are one of the key concepts in physics. We're going to use a capital letter F. Technically, since it's a vector, I should put the vector symbol on it. Why not a lowercase f? Lowercase f is taken by frequency, already used. What are the units for force? Force is measured in newtons, symbol capital N. Or in the imperial system, it's measured in pounds. One of the concepts, Ryder, we're going to be talking a lot about is what we call the net force. The net force is the vector sum of all of the forces acting on an object. It's the total. So don't overcomplicate this. Ryder, if I'm pushing with 5 newtons to the right and 2 newtons to the right, if I wanted to replace that with one single force, what force would that be? Magnitude and direction. Yep. 7 newtons to the right. Or if we wanted to, we could even call one way positive and one way negative and call it +7. But for now, I didn't establish that. Laura, a little more difficult. What's the net force in picture B? I'll give you a hint. It's not 7. How did you get 3 from a 5 and a 2? And in fact, I'm even going to be more specific. What you intuitively did is you said, I should let one way be positive and one way be. And so you said, I'll let the 5, the bigger one, be positive. I'll let the 2 be negative. And you actually could have, although you went 5 minus 2, technically in physics we would say you went +5 plus -2. Whichever way you get there, I agree, it's going to be 3 newtons. Right. Oh, and in this next diagram, what's the net force exactly as a number, do you think, if we have 8 up and 8 down? Loud and proud. When I say loud and proud and you don't speak it any louder, that defeats the purpose. Loud and proud. I'd like you to say it so that YouTube picks it up. That's why I'm asking you to speak up. He's saying 0, YouTube. Yeah, this situation where we have a net force of 0, hugely important. If you know the net force on an object is zero, you'll learn later on there's a whole bunch of other assumptions that we can say are correct, are true. There's a bunch of other statements that we can say. So we're often going to look for a situation where the net force is zero, or what I'll say is where the forces are balanced. They cancel each other out. Okay. Nick, how do you think you'd do part D? What's the net force? It's a trick question. This is what we'll look at in Physics 12. In Physics 12, the first two units are the first, well, really half of Physics 11 done over again, but in two dimensions. We'll learn, okay, it's pretty intuitive, Laura, to say if they're in a straight line, let one way be positive and one way be negative. What if they're at right angles? We'll develop vector mathematics. So that's just a little teaser, a preview of coming attractions, as it were. We need to talk about Newton's laws of motion, and I need to go on my Sir Isaac Newton rant. So sorry, YouTube, I got to pause the video. Put your pencils down, everyone. Look. There are three laws of motion for Isaac Newton. Maddie, I will not make you memorize which one is which, although you can use it as a shortcut to answer a question. You can say, oh, the reason that's correct is Newton's third, and I'll accept that. What you will need to know, you don't need to memorize which one is Newton's third. You'll need to know, though, what they are. You won't need to know which one is first, which one is second, which one is third, but you'll need to know the three laws themselves. Newton's first law is often called the law of inertia. If all the forces are balanced, fancy phrase, the net force is zero, like the one that I was getting Owen to repeat over and over. If all the forces are balanced, Owen, an object will either remain at rest if it was already at rest, or if it was already moving, it'll keep moving in a straight line at a steady speed. Christian, I can summarize that in one statement. If all the forces are zero, A is zero. If forces are balanced, your acceleration is zero. It also works in reverse. If the object is accelerating, the forces cannot be balanced. There must be an unbalanced force. If an object is accelerating, the net force cannot be zero. Remember, accelerating can be speeding up, slowing down, or changing direction. Yep. I don't know, are we? That is Einstein's general relativity view. We're not going to be using that here. We're going to be doing what's called the Newtonian view of gravity. And in that case, Newton would say forces are balanced right now, so you're not accelerating. Okay? He's going to treat gravity as a force. Einstein treated gravity as a curvature, but we're not going to be dealing with that here. We're going to be using what's called Newtonian physics and Newton's laws. Yep, good question. I'd like you to imagine that you're in a car. Your body wants to keep going in a straight line at a steady speed. That's what Newton's first law says. Your body wants to keep going in this direction. It has something that we call inertia. Inertia wants your body to keep going in a straight line at a steady speed. Let's suppose the car makes a quick left turn. What do you feel? You might think that you're getting pushed outwards because you feel the door pressing against your shoulder. That is not what's happening. What's really happening is, since your body is changing direction, there has to be an unbalanced force. The door applies a force on your body. But because you're not used to an inanimate object pushing on you, you think you're getting pushed outwards. You're not. The door is pushing you inwards. What you're feeling is your own inertia wanting to keep going in a straight line at a steady speed. If you're the passenger, you feel the door pushing on you, or you'll have to hold the handle up above your head or something. If you're the driver, you feel it through your arms and the steering wheel, and both of you also feel it a little bit. The seat applies some friction to your bodies, but something has to push you around that corner. So I wrote here, imagine you're a passenger in a car and the driver makes a sudden left turn. What sensation do you feel during the left turn? From your own experience, you might feel like you're getting pushed to the right. You're not. You're wanting to go straight, and the car is having to push you to the left. The driver steers the car to the left. Your body wants to keep going in a straight line, but the door of the car is moving left with the rest of the car, and so your body runs into the door. The door applies a force on you to help you change your direction. Next page. As a rule, Newton's first rule of motion, any object wants to continue moving with whatever speed and direction it currently has. It wants to keep going in a straight line at a steady speed, or if it's at rest, it wants to stay at rest, because 0 is also technically a straight line at a steady speed. When your driver accelerates the car, your body tends to stay where it was, and you feel as if you're getting pushed into the back seat. So if you're sitting at rest at a red light and your driver floors it, you feel like you're getting pushed backwards. Well, no, what's really happening is the seat is pushing you forwards. It has to, because your body wanted to remain at rest. Shahab, I don't know if you remember, but 2 units ago, I told you that our bodies do have a built-in accelerometer, but it's always backwards. I fibbed. Your bodies don't detect acceleration, they detect inertia. They detect your body's resistance to acceleration. And that's why it's always backwards. And in fact, this tendency that all objects with mass have to resist changes in their states of motion is given a special name. Here is your word for today. We call it inertia. Every object in the universe that has mass possesses this property called inertia. Inertia is that thing with mass that resists a force. You can think of inertia as a measure of the stubbornness of an object or its resistance to change. The more inertia an object has, the less willing it is to accelerate. So let's be fairly stupid obvious here. Don't overcomplicate it. Darian, which object do you think has more inertia, a bicycle or a logging truck? Absolutely. Because of that, there are 3 consequences. Number 1, the logging truck is more difficult to get moving. When you're driving, you'll notice if you're ever at a red light behind a semi-truck, the light turns green, the other lane starts to move, the semi-truck slowly starts to accelerate because it has so much inertia, so much resistance to change. It's tough to overcome. Oh, also, Darian, that means the logging truck is more difficult to bring to a stop. It's going to need a bigger stopping distance, and it's not going to go around corners as well. It doesn't want to change direction as well either. It wants to keep going in a straight line at a steady speed. How do we measure inertia? We're going to treat inertia as the same thing as mass. This is only true, Ove, as you raised a point earlier, this is only true if you're not going near the speed of light. Special relativity and general relativity are better versions of what I'm talking about here, but as long as we're not going near the speed of light, this will be pretty good. Inertia, or mass, resists a force. You can think of mass as a measure of the stubbornness of an object. The more mass an object has, the less willing it is to change its motion state. This is why our bodies are backwards accelerometers. Our bodies don't detect acceleration. Geo, we detect our own inertia, our own resistance to a force. That's what our bodies can feel. I wrote here, car accident story. During my student teaching, during my practicum, I got rear-ended by a semi-truck on the freeway. It hurt. It was stop and go rush hour traffic. 2 cars in front of me, someone stomped on the brakes. 1 car in front of me, someone stomped on the brakes really, really fast. I had to stomp on the brakes really, 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 really fast. And behind me, the semi-truck driver had just looked down to pick up his coffee mug. And by the time he looked up, wham, he was into me. I was driving a 1982 Honda. It was an older car. It was a car that had been built when a lot of people still smoked, so it had an ashtray. And what people did back then, if you weren't a smoker, what your ashtray was full of was pennies. We still had pennies back then, and they took up so much room in your pocket. What you would do typically is you would keep the silver in your pocket, but the pennies you would put in the ashtray. And so this ashtray was full of pennies. It had a lot of mass. It was heavy. When I got rear-ended, Owen, the ashtray shot over my shoulder and hit the back seat. No, that's not what happened. I'll illustrate what happened. Here's Mr. Dueck in his car. Here's the ashtray. The ashtray had so much inertia that when I got hit by the semi-truck, me and the car moved forward. The ashtray stayed at rest the way it was. It ended up on my back seat, and it looked to me like it went shooting over my shoulder. No, I got forced forwards by the semi-truck, but it had enough inertia that it ended up on the back seat. In my back seat, I still remember hearing the pennies drop down and fall over my back seat, and then going, ow, that hurt. I'm going to pause the video for a second. Newton's first law says if you're at rest, you want to remain at rest. To cause you to accelerate, you need a fairly big force. And the more mass, the more force. Put your pencils down, look up. This is one I found on YouTube. So these shopping carts are at rest right now. Also, they have a lot of mass, a lot of inertia. They want to remain at rest. This semi-truck driver is about to make a really dumb physics mistake. I could have predicted this right away in 3, 2, 1. Of course, they wanted to stay at rest. Newton's first. That's not my favorite part of this video. My favorite part, watch the guy in the red shirt right here. Keep an eye on him. He's going to look at the mess. And then that look right there where he's scratching his chin. Banner, you're at the very front. What's the timestamp? No, what is... I'm willing to bet coffee break or lunch break starts at 8 a.m. That's the look of somebody looking at the clock and going, can I take my break 3 minutes early? Because I don't want to clean this up. I'm almost certain that's the look I see in his eyes right now. So that was for objects that are at rest. What if you're moving? If you're moving, you want to keep moving in a straight line at a steady speed. So this subway is moving to your left. He wants to keep moving to the left. So the train started slowing down, or I'll say accelerating to the right. His body was touching the bench, and so the bench was able to apply enough force to his body to slow his body down. His head was not attached to his body. His head kept going in a straight line at a steady speed. Newton's first really, Owen, explains outer space. And this is one of the reasons we give Isaac Newton so much credit, is in 1666 he was visualizing outer space at a time when hot air balloons weren't really even a thing. So what does outer space look like? If you're in outer space and there's no forces acting on you, well, here's a nice one. This is the space station getting a reboost.
Here we are at the International Space Station. We're doing a reboost right now, and we're showing that the space station is actually accelerating away from us.
So the backstory here, the International Space Station, although it's in orbit around the Earth, it's not a complete vacuum up there. There's a tiny bit of atmosphere. It gradually slows down a little bit due to air resistance, and so every few months they have to fire some rockets to boost it back up to its original orbit. The rockets are firing out of the screen towards you. So if the astronauts lift their feet
We're going
up,
to float in the middle of the cabin, and it started already. We start off stopped in front of the camera.
Which way are they accelerating? No, they're at rest. We are accelerating away from them. It's all, but yeah, Einstein would say it's all relative. You can pretend they're accelerating backwards. They're staying at rest as the space station and our camera.
The space station is accelerating, leaving us behind.
Yeah, that's yeah. Wow. Wow. Wow.
Mr. Dueck, how come when I see astronauts on the International Space Station, Why are their faces always so red? That's a good question. How come astronauts' faces are almost always quite red? Yeah.
Something.
Nope. Oxygen's fine.
Does it flow?
Your heart is used to having to pump against gravity to get blood to your face and head, and it hasn't made the adjustment. It's sending a little more blood than you need. The other thing astronauts will tell you is you always end up with a stuffy nose the entire time you're there. It turns out gravity clears a lot of the mucus out of your nasal passages. And so food on the ISS, you know when you have a really, really bad cold and your nose is really stuffed and how the food always tastes kind of wrong, the blend, yeah, that's what it is there. The astronauts will tell you they all get a craving for hot sauce. They put hot sauce on everything because that'll cut through the fat. Oh, I could actually get a little taste, but otherwise the food tastes pretty bland. Yeah.
Ooh. That's amazing. I'll do it again. Okay. Floating still. Oh. Wow. Wow. Oh.
They all have engineering degrees, but also they're all 6 years old in their heart. It's because sometimes, Ryder, all you can say is "wow." This Japanese astronaut is one of my favorites. If you take Physics 12 with me, I'll show you a video he made. He came up with an idea to do on the International Space Station that had any of you thought of it, absolutely you would have done that. He's one of my favorites. I'll show you the video in Physics 12 when we look at gravitation. Adam, you with me? You good? Okay. Oh, inertia beads. I got those too. Pause the video. Sorry again for those of you at YouTube. We can't see this. So Newton's first, here's the short version. If an object is accelerating, there must be an unbalanced force acting on the object. Forces cannot be balanced. Oh, and if there's an unbalanced force acting on the object, then that object must be accelerating. It works in both directions. What if it's not accelerating? Forces must be balanced. Remember, acceleration can mean changing speed or changing direction. Oh, I told you force is a vector. I saw Chris Angel do this on TV on his magic show, and I said, no, it's just good physics. I can do this. I got to pause. So, force is a vector. Direction makes a difference. Okay. How does Newton's first law help explain how seatbelts save lives? What if there was no seatbelt in a car crash, Cole? What would happen if you were in the passenger seat, in the front seat? Newton's first, you would keep going in a straight line at a steady speed. That's what Newton's first says. Your inertia would want you to keep going. So I don't want to write a big paragraph here. I'm going to say seatbelt applies unbalanced force to stop us. Now, if you don't have a physics background and you're driving in a car and the driver slams on the brakes, you might say, oh, I was getting thrown forwards. No. You're detecting your own inertia. You were wanting to keep going in a straight line, but what direction is the force acting on you actually? Not forwards. What's applying the force? Starts with letter S. And then an E. Yeah, seatbelt. Okay? Yeah, simple invention. Very simple. Okay, why wouldn't you want a seatbelt on a motorcycle? If they're so good. What's the big difference between a motorcycle accident and a car accident? Yeah. What's the problem with being connected to a motorcycle in an accident? Yeah. How? What does a motorcycle do in an accident that a car generally doesn't? Yeah. No, cars could go that fast. Adam. Yeah. We don't want to be strapped to tumbling wreckage. We thought of that, right? The wreckage will tumble in a motorcycle. Motorcycle in an accident is going to, you would not want to be strapped to a tumbling piece of wreckage. In a car, you're inside a cage, you've got airbags, you've got a roll cage. The wreckage is the wrecked motorcycle. So you don't want to be, the motorcycle in the car accident, it would tend to tumble. You don't want to be strapped to it as it tumbles. Bouncing, bouncing along. In a motorcycle accident, it's going to bounce. Almost certainly. I'll show you a video of one a bit later today. No, next class. Christian, you good? What do you yell when you want the front seat? Why? Just dumb. Why shotgun? What's the history there? So the original expression comes from the old stagecoach days. Back when stagecoaches were the main means of hauling things back and forth, they were often carrying payroll, money. And so the driver would sit on the left-hand side holding the reins, and next to him would be a guard with a shotgun sitting in the shotgun seat. So that's where the original expression came from. But I grew up without seat belts. What we used to say is, shotgun, if there's an accident, I'll be the first one out to inspect the damage. That was our ghoulish joke. In other words, if we are in a head-on collision, I'm going through the windshield, I'll end up on the hood, I'll be the first one to see the damage because I'll be sitting there dead, but I'll be the first one there. That was our joke. Let's do some basic physics here. It says this. Turn the page. Manuel weighs 1,000 newtons. That means gravity pulls on Manuel with 1,000 newtons. And he stands in the middle of a board that weighs 200 newtons. The ends of the board rest on bathroom scales, and we'll assume the weight and the board of the board and the person act at its center. It says fill in the correct weight readings in this scale. We can handle this, no problem. Tristan, take a look at this person. First of all, what's the total force downwards in newtons? Do the math in your head. Okay. Is this person sinking into the ground like quicksand? Say no. Are they flying into the air like Superman? Say no. Are they accelerating at all? That means forces must be, I'm looking for a word that starts with letter B and rhymes with balanced. Forces must be balanced. What's the total force down? You just told me. What must the total force up be then? How much is each scale pushing up with then? No, because 1,200 plus 1,200 is 2,400. How much each scale must each scale be pushing up with then? So the total force up is 1,200. Yep, loud and proud. Yes. Has to be. If not, then he would have to be, the whole system would have to be accelerating if it wasn't balanced. Okay, Alexia, a little trick here. Still 1,200 newtons down. Look at the picture. Is this whole system sinking into the ground like quicksand? So, no. Is it flying through the air like Superman? So is it accelerating at all? So that must mean the forces are, I'm looking for a word that starts with letter B and rhymes with balanced. What's the total force down? 1,200. This one is pushing up with 850. How much must this one be pushing up with? You can use your calculator or do it in your head. What are you going to type on your calculator, Alexia? I know, that's why I'm picking on you. You're zoning out. You're back. What's the total force down? As a number? 1,200 total. So what must the total force up be? Same answer. Here's 850. How much must this one be pushing up with? What are you going to type? Yes. Which I'm pretty sure, check me if I'm wrong, 350? Okay. Yeah. No. Tip up? No. Yeah, look where he's standing. We're good. Now, if there was more to the board over here and he stood over, that's a whole different situation. Then we have something called torque, physics 12. I'm picking these very carefully to avoid certain situations. Then it might start to spin. Ooh, let's look at some bridge physics. Okay, it says a 12-ton truck is 1/4 of the way across a bridge that weighs 20 tons. So, okay, Nick, is this bridge accelerating down? I hope not. Is this bridge accelerating up? No. So, what's the acceleration exactly as a number? Which means forces must be, I'm looking for a word that starts with letter B. Okay. What's the total force down? You might be able to do it in your head. What must the total force up be then if we're not accelerating? This is 13. How can I figure out how big that one is? How'd you get that? You're right. Yep. Got to be 19 tons. So you can start to look at how strong bridge supports need to be. In terms of Newton's first law, the law of inertia, how does a car headrest help to guard against whiplash in a rear-end collision? How does it guard against? Yeah. Well, I'm going to be fussy. Your head doesn't go all the way back. Your head remains at rest. What gets pushed forwards? Your body gets pushed forwards. I got to be fussy. You said your head goes back. No, it doesn't go anywhere. It stays where it was. If you come to a stop, your head is going to stay stopped, but the seat pushes on your body, pushing you forward. Your head stayed at rest. You'll feel like it snapped back, but actually your body snapped forward. And there's an easy prevention. Adjust your headrest. And I'm being very serious now to all of you as the physics teacher who cares about you. When all of you buy your first car, every time you get a new car, first thing, it takes 30 seconds. Adjust the headrest. Make sure it's the right height. You can save yourself a lifetime of pain with that 30 seconds. You can go from massive injury to owie. You'll be sore for a day, but you won't be sore for years. Okay? So, headrest applies force to head, comma, keeping it with body. I got to be fussy, Ryder. You said your head snaps back. No, it doesn't. Your body pushes forwards. Pause the video for a second. The first 2 weeks of July every summer, we've rented a house on Gabriola Island, a beach house. And we go there and we have barbecues and we read and we relax. And a couple of times, one of our friends is on the Coast Guard dive team. We've invited them to bring their hovercraft from the mainland over for a barbecue. So this is the Coast Guard's big hovercraft. So this one, those are people, to put it in perspective. This one's really loud. Can pass cars on the freeway on land. They'll shred the skirt, they'll do damage, but they're authorized to do that if it's life and death. And so the big advantage with those, especially, in fact, they had just been to Gabriola Island 2 days earlier. A father and daughter were hiking along the beach. The daughter, I think, was 13 years old, and she was walking between two logs, and she slipped, her leg slipped down, and she snapped her leg sideways and broke it. And the tide was coming in, and there was a whole bunch of logs between the shore, and the father was not able to carry his daughter over there. Coast Guard came across. They could go right over the logs, right over the rocks. They dropped a stretcher right in front of her, and they were pretty matter of fact. Oh, she's 13. Back at that age, she'll be fine. Her bones will knit in 2 months, and she'll be turning cartwheels. If it was an old person, they'd be limping for the rest of their life, but she'll be fine. So you guys still heal pretty quickly. How fast will this box accelerate? Let's see if we can figure it out. So, Arnica, how big is the applied force pushing forwards? 75 what units? Newtons. We'll repeat that just so an easy way to remember the stupid units is to repeat them. How big is friction pushing backwards? What's the net force exactly as a number? So forces are, I'm looking for a word that starts letter B. What's the acceleration exactly as a number? Anybody here getting their pilot's license? No? Anybody here getting their pilot's license? That's what I asked. Yeah. Oh yes, I've had several students coming through that are getting their pilot. And there's one this year that didn't tell me until afterwards. So, Ryder, in a standard airplane, I'm going to ignore the vertical forces, but horizontally, you have drag and thrust. If drag and thrust are equal, Ryder, what's the acceleration of this airplane exactly as a number? Because forces are, I'm looking for where that starts letter B. There you go. That's what Newton's first says. What if thrust is larger than drag? Which way must this airplane accelerate? Banner, which way must this airplane accelerate if thrust is bigger? Forwards. And what that will also do, since it's accelerating forward, since it's speeding up, that will create more lift. It'll gain altitude. What if drag is bigger than thrust? What if thrust is smaller than drag? Which way will the plane accelerate? Backward. And we're going to call it acceleration. We rarely use deceleration in physics. The public does, but not in physics. So it's going to accelerate backwards. And as a result, lift will also decrease. You'll lose altitude. So one of the basic ways you can control a plane's altitude is just with your thrust. By adding and removing the amount of fuel going to the engine, you can control a great deal of the airplane. Oh yeah, I wrote here, by controlling the throttle, how much fuel is supplied to the engine at any one time, you can control the acceleration, you can control the lift, you can control much of the altitude. A couple more, we're done. Turn the page. Newton's second law is the equation. It tells us how to calculate force. We're almost done. You guys rode the hovercraft more than most. That's fine. The equation says this, F equals ma. Can you all find that? Oh, and force is a vector, acceleration is a vector. Can you all find that on your formula sheet? Should be on the front page about halfway down, not quite halfway down, about a third of the way down. Is that right? Christian, does that mean you need to memorize it? You should. I'm doing you a solid. If you're going to be looking this up 150 times in the next few weeks, you want to memorize F equals what? Ma. F equals what? Everybody. Ma. What F equals what? Everybody. Ma. Where M is the mass in kilograms and A is the acceleration in meters per second squared. By the way, this also means that a Newton is technically a kilogram meter per second squared. Ma. And in fact, Alexia, that's how we described force for quite some time. But then the International Convention of Weights and Measures about 100 years ago decided to name that a Newton after Sir Isaac Newton. Malcolm has a mass of 65 kilograms. You know what? Let's change this from Malcolm. Cross out Malcolm. Let's put the word Tristan right there. We're going to use Tristan as our guinea pig. What's the magnitude of the gravitational force acting on him? Okay. Solomon, what's this asking me to find? The gravitational force. So we would start out, well, F equals what? Ma, write that down. Except, you know what? Really lightly cross it out. I'm going to modify this. For gravity, I'm going to use F with a subscripted G for the force of gravity. And I'm going to say it's mg, where g is the acceleration due to gravity. We'll go straight to that punchline. So what's the mass of Tristan in this question? 65. And what's the acceleration due to gravity? You've probably still got it memorized from a couple of units ago. And we're not going to use the negative here. We'll just use the 9.8 because it said the magnitude. How hard is the Earth pulling down on Tristan? Good to see that all of you had got your calculators out at the beginning of class when I was yelling at you to get your calculators out at the beginning of class. Not that I'm mentioning any names, but I'm holding some serious grudges. Christian, what'd you get? 637 units? Units? It is. It's right up there. Except we don't call it it'd be a kilogram meter per second squared. What? Sir Isaac Newton. Yeah, a Newton. Okay. By the way, gravitational force has a special name. We call it weight. In physics, weight is not measured in kilograms, that's mass. Weight is how hard gravity is pulling on you, which means, Darian, your weight will change depending on what planet you're on. Your mass won't change, but on the moon, G is smaller, you'll weigh less, same mass. On Mars, G is smaller than the Earth, you'll weigh less, same mass. Weight changes, it's location dependent. Mass is the same anywhere in the universe. Tristan stands on his lab table. Tristan stands on his lab table. Tristan stands on his lab table. Tristan, oh, he's figured it out. Tristan stands on his lab table. You get to indulge your inner stands. You're fine. You won't hit the ceiling. Oh, you are a little taller. Okay. Tristan's enjoying his inner 5-year-old that always wanted to do this, glaring down at everybody. But here's what the question asks. What's the magnitude of the upward support force that the table exerts on Malcolm? This is important, so focus in, Adam. What's the magnitude? You know what? We're going to draw a little picture. Represent Tristan over here with a dot. What are the forces acting on Tristan right now? Get the obvious one. It starts with letter G. Gravity this way. I'll put a little FG with an arrow like that. But look at Tristan right now. Is he sinking into the table like quicksand? Everybody say no. Is he flying into the air like Superman? So is he accelerating? That means forces must be, I'm looking for a word that starts with letter B. So I know there's an arrow pointing up. Draw it the same size as the one pointing down. Something's pushing up. What force is pushing him up? Banner. Now, Tristan doesn't notice it right now. Tristan, stand on one foot. Now you can feel the table. Now your brain says, oh, something changed. You can feel the table pushing up through your feet. When you're standing or sitting, your brain tends to tune out the thing pushing up on you, keeping you from sinking into it. But as soon as you change that a little bit, your brain says, oh, now I notice it. Yeah, on your diagram, let's call this F table. Thank you, Tristan. You can sit down now. So based on that, as a number exactly, how big is F table? No, 9.8 is an acceleration, not a force. That's a bad guess. As a number exactly, how many newtons is F table? What? Of course it is. If it was 638, you would be accelerating up because that's where the unbalanced force would be. If it was 636, you'd be sinking down into the ground like quicksand. And in fact, when something breaks when you stand on it, that's what's happening. It was unable to exert a big enough force to counteract your gravity, and so because it couldn't match it, you accelerated down, you broke the object. I just thought it broke. Yeah, some good physics there. Part 2 says, how do we know this force exists? A equals 0, so forces are balanced. However, moving forward, if you just wrote Newton's first, I'd accept that as a full answer. You don't have to memorize which one of Newton's laws is which, but you can, and you can use that to give a shorter answer than having to write out the law in English. By the way, this diagram right here is a very, very important diagram. We call this a free body diagram. And that's probably the most important tool that I will give you in this unit. In fact, often you're going to hear me when you ask me a question, I will reply, I think this is a good job for a free body diagram. This will be one of our go-tos. We'll use a free body diagram to figure out all of the forces acting on an object. We'll write an equation for the net force, and the net force equals F equals what, everybody? F equals what, everybody? MA. We're going to pause here. If you want to get a head start on the homework, because I haven't finished the lesson, your main homework is study for the test. But right now, you're capable of doing, if you turn the page to where it says Part 1, Newton's Laws, where there's a little picture of the girl on the swing. You can circle number 1. Number 1 says, little Nellie Newton wishes to be a gymnast. It says she weighs 300 newtons. In other words, gravity is pulling down with 300 newtons. Is she accelerating downwards in the picture? Geo, say no. Is she accelerating upwards in the picture? Say no. Say no. So that means the forces are balanced. How hard must the rope be pulling up in picture A exactly as a number? Got to be 300 newtons. What if we have 2 ropes? How hard must each rope be pulling up? Don't say 300. 150. So that's, see if you can take the rest of it from number 1. You can also do number 2, number 3, number 4. I put the answers for that at the bottom of this page. You can also do 5, 6, 7, 8, 9, and 10. This is not homework yet. This is homework after the next lesson, which won't be, I'll finish this lesson off on Monday, and you'll get a lot of time in class to work on it. Although on Monday, the classes will be shorter again because we'll be going back to unforced flex as far as I know. Thank you for your patience.